In the last few lectures, we had examined examples of solutions for transport in one direction, that is unidirectional transport, using what is called a similarity solution. Okay, where we had, in general, we had wanted to solve the unsteady conduction or the concentration equation is equal to alpha partial square t by partial z square. And in these similarity solutions, because there was either transport into an infinite medium, either a surface whose temperature was instantaneously increased, bounding a medium in a semi-infinite half space, or in an infinite domain some a pulse of some species injected instantaneously into at the plane. Okay. In both of those cases, we were able to reduce it to a similarity solution using the transform z by root alpha t is a dimensionless variable, a dimensionless group, okay, which contains both of these coordinates. And when the equations and the boundary conditions were expressed in terms of these coordinates, the resulting equation and the boundary conditions were only a function of xi alone and not separately on z and t. And using that, we converted from a partial differential equation to an ordinary differential equation, and then we solved these problems. The most recent example we have seen is one where there is heat conduction, okay, into a fluid, all right, okay, which is a material that is melting, and it has a solid phase here and liquid. The solid is at the melting temperature. So, therefore, at this surface z is equal to h, T is equal to the melting temperature, and at z is equal to 0, T is equal to some temperature which is greater than Tm. Due to that, you have conduction of energy, okay, due to the temperature gradient from T naught over here to Tm over here. And there also we found that provided we specify the temperature T naught at the boundary, we can reduce the problem to one of a similarity variable z star is equal to z by a time dependent length scale, and we could get a similarity solution. I will now solve one final problem on similarity solutions in order to show you that it can be applied to curvilinear coordinates as well, but it is limited. Okay. It is limited to particular configurations in a curvilinear coordinate system, and that is heat conduction from a thin wire. Okay. I have a wire within an infinite medium. Okay. So, this wire, okay, along the z direction. Okay. So, this is the z direction. Okay. It is of infinite height in the z direction, which is heated compared to the ambient, which is at a temperature T infinity. Okay. And this wire generates heat energy, okay, which then is transported radially outward from this wire, which is the axis here of this coordinate system. Okay. And we want to find out how the temperature varies with time. So, the configuration is that T is equal to T infinity, okay, for the distance r going to infinity, the distance from the wire going to infinity, and T is equal to T infinity at T is equal to 0 for r greater than 0. That is just before the heating has started. The temperature is T infinity throughout the domain. Okay. Now, if I look at this in the plane perpendicular to the z axis, okay, if I look at it in the xy plane, this is x and this is y, and my wire is at the origin perpendicular to the plane. Okay. The wire is the origin perpendicular to the plane. Okay. So, I should consider a coordinate system in which x and y vary, okay, from positive to negative values. So, let me just redraw that. This is the location of the wire, and it is generating a certain amount of energy per unit time. Okay, it's generating a certain amount of energy per unit time. Okay. The temperature of the wire and the surrounding fluid is T infinity at T is equal to 0, and then the wire is instantaneously switched on. Okay. And it generates an energy per unit area per unit time, which is Q. Okay. The wire generates an energy per unit time, which is capital Q. Okay. So, now how do we solve this problem? The wire is of infinitesimal thickness, so there is no length scale associated with the wire itself. Okay. The conservation equation, okay, partial T by partial T is equal to, this is now in a cylindrical coordinate system, okay, where r is the distance from the origin to an observation point, and I will choose phi as the angle, okay, in the polar coordinate system. In this particular configuration, there is no dependence on the angle phi because it is completely axisymmetric. The wire is at the center and it is generating energy only radially outward. Okay. So, it is an axisymmetric coordinate system. Okay. Recall that the conservation equation in this case is alpha del square T. Okay. And when there is a variation only in the r direction, there is no variation in either around the wire or along the wire. Okay. Then this becomes equal to alpha into 1 by r d by dr of r partial T by partial r. So, that is the conservation equation. Okay. Now, there is no particular temperature scale in this problem as stated. Okay. So, what I have is that the temperature goes to 0 far away, and then I have this one condition on the energy generated per unit time. Okay. So, the temperature scale has to come out of this energy per unit time. I will show you how that comes out, but for the present we can just define the temperature, scale temperature, as T minus T infinity. Okay. So, that the scale temperature is equal to 0. Okay. So, the boundary conditions reduce to T star is equal to 0 for r going to infinity. Okay. And the heat flux, okay, so energy per unit time heat flux, that is minus k, okay, partial T by partial r. Okay. Note that the energy per unit time, I have said, I will write it over here, energy per unit time is equal to Q. Okay. The energy per unit time at the wire. Okay. So, recall that the wire is of infinitesimal thickness. Okay. It is basically having infinitesimal thickness. Okay. This energy per unit time is going to be equal to, in the limit as I go close to the wire. Okay. I will plot that in larger over here. Okay. In the limit as I go close to the wire, okay, in the limit as r goes to 0, the energy per unit time is this flux, okay, is this flux QR. Note that it is radially symmetric. So, it is this flux QR times the area. Okay. The area is the product of this perimeter, okay, the area is the product of this perimeter, okay, multiplied by the height of the wire, okay, multiplied by the height of the wire. Okay. So, if you assume unit height for the wire, okay, if you assume unit height for the wire, okay, and assume that Q is the energy per unit height. Okay. So, Q is the energy generated per unit height of the wire per unit time. Okay. So, I should write this as energy per per unit height into time. Okay. Energy per unit height of the wire into time. Okay. So, this has got to be equal to QR times 2 pi times R. Okay. This has got to be equal to QR times 2 pi by times R. Okay. So, here I have, okay, as for R going to 0, okay, QR times 2 pi R. Okay. QR from Fourier's law of heat conduction is minus K partial T by partial R into 2 pi R, okay, is equal to the energy that is generated from the wire per unit height in the z direction per unit time. Okay. This is for R going to 0. Okay. For R going to 0, I do not have a constant temperature on the wire. What I have is a constant energy generated per unit height of the wire per unit time. Okay. The constant heat generated per unit height of the wire per unit time. So, these are the two boundary conditions as R goes to infinity and R goes to 0. Okay. And the initial condition is that T star is equal to 0 for R greater than 0 at initial time at T is equal to 0. Before you have when you have just switched on the heating of the wire, the temperature everywhere is just equal to 0, T star is 0 or T is equal to T infinity. So, these are the boundary conditions that I have to use, boundary and initial conditions. Now, I do my reduction to an ordinary differential equation using the fact that there is no length scale in the problem, okay, using the fact that there is no length scale in the problem. Okay. If there is no length scale in the problem, I can define psi is equal to R by root of alpha t. Okay. Psi is equal to R by root of alpha t. Okay. Therefore, partial T star by partial R is equal to 1 by root alpha t, partial T star by partial psi, partial square T star by partial R square is equal to 1 by alpha t, okay, and partial T star, okay, by partial t. Okay. These two come out straightforwardly because psi and R are just there is only a factor of root alpha t between the two, okay, is equal to partial T star by partial psi by partial t, okay, into minus R by root alpha t power 3 by 2. Okay. I have a t power minus half, so this should have a factor of 2 here. And R by root alpha t is of course equal to psi. So, therefore, I will get, my apologies here, this should be psi, okay, is equal to minus psi by 2 t dt by d psi. Okay. And these all should be total derivatives because our postulate is that once you express everything in terms of psi, it depends the temperature field is only a function of psi and not individually of R and T. Okay. Okay. Substituting that into the conservation equation. Okay. So, the conservation equation is partial T star by partial T is equal to alpha into partial square T star by partial R square plus 1 by R partial T star by partial R. Okay. Substituting this, we get minus psi by 2 t d T star by d psi is equal to alpha by alpha t into d square T star by d psi square plus 1 by psi dt star by d psi. and the t's will cancel out on both sides, the alphas will cancel out on both sides. Okay. And I can just rewrite this equation as d square t star by d psi square is equal to minus or rather plus psi by 2 plus 1 by psi. This is equal to 0. So, this is the governing equation, okay. And I also have to express the boundary conditions, okay. Okay, the boundary conditions and the initial conditions, okay. So, first one, as r goes to infinity or as t goes to 0, okay. In both of these cases psi goes to infinity, okay, t star is equal to 0 as psi goes to infinity. Okay. So, the initial condition and the condition as r goes to infinity turn out to be the same. Okay. The second condition is what we had there, okay, what we had over here. Okay. As r goes to 0, minus k into partial t by partial r into 2 pi r is equal to q. Okay. Substituting r is equal to psi is equal to r by root alpha t, you can see that the factor of root alpha t in the denominator and numerator will cancel out when I express r in terms of psi. Okay, when I express r in terms of psi, numerator and denominator, the factor of root alpha t will cancel out. Okay. So, the resultant equation is just minus k 2 pi psi dt star by d psi is equal to q. Okay. So, that is the condition in the limit as r goes to 0, okay, or psi goes to 0. R goes to 0 corresponds to psi goes to 0 in this case. So, these are the two boundary conditions in the psi coordinate. Psi goes to infinity, the temperature has to decrease to 0, which is either r going to infinity or initial time, and psi goes to 0, you have this expression which basically reduces to psi times dt star by d psi is equal to minus q by 2 pi k. Okay, so, this is the boundary condition in the limit as r goes to 0. Okay. So, this equation can be solved. Okay. So, this equation can be solved. Okay. These d square t star by d psi square is equal to minus of psi by 2 plus 1 by psi dt star by d psi. Okay. I define dt star by d psi is equal to some new factor w, and this gives me the equation dw by d psi is equal to minus of psi by 2 plus 1 by psi, okay, times w, okay, or cross multiplying, okay, dw by w is equal to this into d psi. Okay. Solution, natural log of w is equal to minus psi square by 4 plus natural log of psi, okay, plus a constant c, or let me call this as a, okay. Taking the exponential of this equation, On the left side I will just get W is equal to, which is dt star by d psi, is equal to, there is a mistake here, it should be minus log psi, okay, because you can see that the negative sign multiplies both of these, okay, the negative sign multiplies both of these, okay. Okay. So, exponentiation of minus log psi is 1 over psi, okay, into e power minus psi square by 4, okay, into e power a, which I can write it as another constant, that is c. Okay. So, this is dt by d psi. Okay. What is t? Is the integral of this. Okay. T star is equal to c integral d psi into 1 over psi e power minus psi square by 4. Okay. Inside the integral sign is the dummy variable, the variable of integration, okay, and I have to have upper limit of integration as psi, okay, upper limit of integration as psi, okay, plus I will have another constant d here when I do the integral. What should be the lower limit of integration? Okay, it can be anything. Okay, changing the lower limit of integration only changes this constant d. Okay, changing the lower limit of integration only changes this constant d. Okay. I know that t star is equal to 0 as psi goes to infinity. Okay. T star is equal to 0 as psi goes to infinity. Okay. Therefore, if I do the integral from infinity to psi, okay, then this constant d will automatically be 0, right, because t star is equal to 0 when psi is equal to infinity, and that integral from infinity to infinity is basically 0 because the limits of integration are the same. Okay. So, this d will be equal to 0 in this case, and this satisfies the boundary condition as psi goes to infinity or as r goes to infinity. Okay. So, this setting this constant to 0 satisfies the boundary condition in the limit as r goes to infinity or as psi goes to infinity. How do we determine the constant c? Okay. Recall that we had the condition here. Okay. Recall that we had this particular condition. Okay. This particular condition. Okay. Okay. Psi dt star by d psi is equal to q by 2 pi k. Q is the energy generated per unit height of the wire per unit time. Okay, Q is the energy generated per unit height of the wire per unit time for r going to 0. Okay. We have the expression for d psi by dt over here. Okay, we have the expression for d psi by dt over here. Okay. D psi by dt is equal to, okay, c by psi e power minus psi square by 4. Okay. That whole thing multiplied by psi is equal to q by 2 pi k for r going to 0. Okay. And you can see even though psi goes to 0, okay, so this is basically r going to 0, which corresponds to psi going to 0. Okay. Because psi is r by root alpha t. You can see that in the limit as psi goes to 0, these two terms cancel out and the exponential just gives me 1. Okay, so I get c is equal to, I have a negative sign missing here. Okay, so, okay. Note that in this expression there is a negative sign here, so I should add that over here. C is equal to minus q by 2 pi k. So, this gives us an expression for the temperature field. Okay. T star is equal to minus q by 2 pi k integral infinity to psi d psi prime 1 over psi prime e power minus psi prime square by 4. Okay. This is the temperature field, okay. And the flux q r is equal to minus k partial t by partial r, okay. It's equal to minus k by root alpha t partial t star by partial psi. Note that t star is just t minus t infinity and t infinity is a constant, okay. So, this will basically give you minus k by root alpha t, okay, into dt star by d psi is given by minus q by 2 pi k, okay, minus q by 2 pi k psi e power minus psi square by 4. Okay. This is the heat flux, okay. And I could write it back in terms of the original variable r. So, this will just give me q by 2 pi r e power minus r square by 4 alpha t. Okay. So, that heat flux increases proportional to 1 over r as r goes to 0. As you go closer and closer to the wire, heat flux increases proportional to 1 over r, okay, and heat flux is the derivative of the temperature with respect to r, which means that this T star is proportional to log of r, okay, as r goes to 0. Okay. It should be actually minus log of r because there is a negative sign here. Okay. So, if I plot the temperature as a function of radius, I get something that T star as a function of psi, okay, I get something that decreases quite rapidly, okay, and it decreases below about 0.01 for psi approximately 3.26. Okay, so, it decreases very rapidly within about 3.26 times root alpha t, that is the penetration depth. This temperature comes to about 1% of its actual value. Okay. At the wire itself, the temperature is diverging. Okay. That is because we have assumed it to be of infinitesimal thickness. In reality, the wire will have some thickness, okay, and therefore, this sharp increase will get cut off when the distance, when the radial distance becomes comparable to the thickness of the wire. Okay, that at that point, this temperature increase will get cut off. Okay. In the approximation of an infinitesimal wire, the temperature increases as minus log of r. Okay, log of r is negative for r small. So, it increases proportional to minus of log of r. Heat flux increases proportional to 1 over r as r goes to 0. However, heat flux times the area. In this case, it is the perimeter times the height. Perimeter is 2 pi r. Okay. So, heat flux times 2 pi r is finite. Okay. That is the heat transferred per unit time per unit height. Okay. The heat transferred from the wire per unit time per unit height, that is a constant. Heat flux itself increases proportional to 1 over r in this approximation, and the temperature increases as log of r in this approximation. So, this is one more example where we could use similarity solutions in order to find out the temperature field. Note that in the case of a Cartesian coordinate, we could assume that the temperature along a plane was a constant, or the material was injected along an infinite plane. In this case, we have to assume that there is an infinitesimal wire of infinitesimal thickness located at the origin in this cylindrical coordinate system. Okay. An infinitesimal wire that is located at the origin in this cylindrical coordinate system in order to solve for the temperature field. Okay. So, this completes our discussion of similarity solutions. I have solved various kinds of problems for you in the broad area of similarity solutions, both in Cartesian and in cylindrical coordinates. Okay. In the next lecture, I will start discussing problems where there is a length scale in the problem, okay, where you cannot assume that there is a similarity solution because there is no length scale. Okay. There is actually a length scale in the problem. In those cases, how do we solve transport problems? Okay. That I will start in the next lecture. I will see you then.